Welcome. Today, we're going to expand on the idea of the work and power lecture that I gave yesterday to talk about work and concentrate more about energy. Okay. You can follow along with this PowerPoint, but unfortunately, none of the animations work if if you don't actually have PowerPoint. So you'll have to come back and look at this awesome video. Okay, so the way this is set up, this note sheet this is like the world's lamest roller coaster, right? So tick, tick, tick up to the top, all right, and then you slide down, and then you're stopped by a spring. And we're going to examine the different kinds of work and energy that go into riding the world's lamest roller coaster. Okay, so here we go. Let's start with a definition, and that's mechanical energy. So mechanical energy is specifically potential and kinetic. And we're going to learn there's two types of potential, and then there's kinetic energy. That is to separate it from all the other kinds of energy, right? Like light energy and sound energy and electrical energy. And I don't know, think about a million other things kinds of energy. Internal energy, right? Specifically in physics, we're going to concentrate on the mechanical energies, okay? All right. So how do you get to and also just to remember that both work and energy, they're two sides of the same kind of thing. So they're both measured in joules, abbreviated with a capital G, and a joule is just a Newton meter. Okay. Now, how do we get to the top? How do you put energy into a system? All right. And that is you do work. You apply a force over a distance. As we learned in the last lectures, there's some caveats in that, like that this simple formula assumes that both the force and the distance are parallel to each other. Okay. But when you do that, when you apply a force through a distance, you change the mechanical energy in a system. All right. So this work is equal to the change in energy total, and ET stands for energy total. Okay. Now let's look at these three different scenarios. Okay. So you'll notice that there's trucks going up three different ramps, and they're all at different angles. Okay, look at which things are the same and which things are different about each of these. Okay, all right, so as they go up, you should notice that the steeper the hill, the larger the force. That's not surprising, right? It's harder to climb a steep hill than a shallow hill. All right, notice that the displacements are different. Okay, that the steeper the hill, the shorter the displacement to reach the same kind of height along the ramp. And then also notice the works, and the works are the same in all three. All right. And the reason is that trade-off we talked about in the last lesson, right? If there's an increased force in this simple machine, this ramp we're using, then there'll be a decreased distance. Or if there's a decreased force, there'll be an increased distance, right? So there's that trade-off. But the work is the same in all the scenarios, assuming there's no friction, like difference in friction from each of these. Okay. All right. Now, let's talk about energy, the different kinds of mechanical energy. So gravitational potential energy is the energy that's associated with position in a gravity field, right? You might have heard that potential energy is stored energy, but really it's energy due to position, right? So you have different, depending on your position in a gravity field, you have different amounts of energy, okay? The higher you are, the more potential energy you have. Now, a couple things to warn you about there. Do you have any potential energy now? All right. Do you have any height now? Right? Like I'm sitting on a chair. If someone pulled the chair out from under me, I'd fall. All right. If there was a hole in the floor, I'd fall into the basement. Right. So basically, you have to decide where the ground is when you use this formula. Your reference table gets around this by putting a delta in. So they don't have the formula that's written here. They just have delta PE equals mg delta H. And they're reminding you that the change in PE is directly related to the change in height. Okay. At the top of the roller coaster, they've got the maximum PE. And actually, this is also a really useful time. It's actually really useful when we're problem solving to determine where you only have one type of energy. And at the top, imagine you're on this roller coaster, you made it to the top, and you're kind of waiting to fall, but you're at rest. Then the only type of energy you have there is PE. Okay? All right. Now, as you slide down the roller coaster, you get energy of motion, which is KE. And we played around a little bit with that in the momentum unit. KE is equal to 1/2 mv squared. All right, so notice that velocity is the most important part of kinetic energy, and that is because it's squared, right? So if you double the velocity, you quadruple the kinetic energy, okay? This, by the way, is the reason that they teach you in driver's ed that if you double your speed, your stopping distance is 4 times as long, all right? That basically comes back to that idea, this squared thing here. Okay. Now, on our world's lamest roller coaster, way at the bottom, when you're at the bottom and you don't have any height anymore, but you haven't slowed down because you haven't touched the spring yet, then you have all of your energy is in the form of KE. Okay. All right. Halfway down, you have a mixture of both KE and PE. In fact, this whole time, as you go down, the PE is going down and the KE is going up. Okay. So there's lots of times when you have more than one kind of energy. And then finally, the last type of mechanical energy we're going to talk about this year is the potential energy of a spring. Sometimes we call this elastic potential energy, but your reference tables calls it PES, potential energy of a spring. And that's equal to 1/2 kx squared, where k is the spring constant. Now, warning, little k is one of the few little letters that they use twice for 2 different things. It is both the electrostatic constant, which is on the front of your reference tables, and also k is used for a spring constant. And the spring constant is a measure of how stretchy a spring is. So if you think about like taking apart a pen and pulling that little spring out of there, that would have a really low k. And then if you think about one of those like hand exercises that you have to like squeeze really hard, that's a k with a really high a spring with a high K. And in your lab today, you're going to be playing around with finding the spring constant of a spring by doing a little lab and using this formula here, F equals Kx. All right. And this little formula basically says that the force you need to stretch a spring is dependent on both the stretchiness of the spring constant, and X, which is the stretch or elongation of the spring. Some springs store energy on stretch and some store energy on compression and some store energy in both, and it kind of just depends on what kind of spring you've got. All right, so 2 formulas here. This F equals Kx, it just shows the relationship of force and stretch, and then the potential energy of a spring, which says that the potential energy is 1/2 kx squared. One other thing I want to warn you about. Most of this year we've been doing constant forces, right? Like a constant force of gravity on you, or we apply a constant force in a lab. Springs are not constant forces. The more you stretch the spring, the harder it is to stretch it further. Okay? That's what this law is saying right here. So just a warning that this is not a constant force like every other force that we've had. Now, we're going to talk a little bit more about this next time, but basically, I just want to state this idea that energy changes form, not amount. That's the law of conservation of energy. The energy changes form, not amount. Now, one caveat, remember energy and mass are really the same thing, so it's really conservation of mass/energy, but in physics class, the mass is not going to change significantly. We couldn't measure the tiny, tiny amounts of mass that are turning into energy. Okay, so just keep thinking energy changes form, not amount. So what that means is that if you needed 10 joules of work to get you to the top of this hill, then you would have 10 joules of potential energy at the top. You would have 10 joules of a mixture of potential and kinetic all the way down, right? And the potential would be dropping, the kinetic would be going, till you got to the bottom of the hill, okay? And then you'd have 10 joules of kinetic energy. And then when you hit the spring and compress the spring, all right, imagine you stopped it right there when the spring compressed, then the spring would have 10 joules of spring potential energy stored in it, okay? Energy changes form, not amount, okay? I'm going to talk a little bit more about this, and then we'll talk about how to problem solve with conservation of energy next time. Okay, so let's look at some places where energy is conserved. And just like in the momentum unit where we kind of separated things and we're like, all right, if there is a force applied, it's not a closed system, and the impulse causes a change in momentum. But if there's no force applied, you have a closed system, we have conservation of momentum. And the same thing's kind of going to happen here. If we have a closed system where we're not doing any work and applying any forces, then the total energy is going to stay constant, like the momentum did. All right. But if we do have work, then that's going to change the energy the same way that doing applying a force for a certain amount of time caused an impulse that changed the momentum. All right. So let's look at some different examples. All right, so we have a little roller coaster here, not the world's lamest roller coaster. And notice that we've got some energy bars, and you saw some of this in your labs. So there's a KE, a PE, and a total mechanical energy. That's green, okay? And you'll notice that as they go along, the KE and the PE trade off, but the total mechanical energy does not change, okay? Notice that it has maximum PE when it's at the top of the hill, maximum KE at the bottom, and whenever it's at the bottom again, it has that maximum KE again. Energy is what's called path independent. It doesn't matter what happened on your way. It just, like, you can look at any moments in time and kind of tell everything about it. It doesn't matter that the roller coaster went through a loop before it hit the ground again and had that same energy. This, of course, is all assuming that there is no friction lost. If there was friction, this would not be a closed system, and the total mechanical energy would go down. Okay. Let's look at a pendulum, and you did a whole lab on that. All right. Notice at the top, it has PE. At the bottom, it has KE. Okay. And then notice that the PE never goes all the way to 0. And that's because they're counting the ground as way down here. And the pendulum never actually gets all the way to the ground. Okay? All right? So that's why the PE never gets all the way down to 0. Okay? How does the PE at the top compare to the KE at the bottom? Well, the PE lost is equal to the KE gained and vice versa. Okay? All right, and hopefully you saw that in your lab as well. And then we have a dart, okay? And again, we have 3 things here. So we have potential energy of a spring. So this is a spring-loaded dart gun. All right, we have KE and we have PE. By the way, a lot of times we just say, when we say PE, we're assuming that you mean gravitational potential energy. And then with spring, we actually have to say elastic or spring potential energy. But if you just say PE, we're usually assuming you mean gravitational PE. Okay, so look at these better. And then notice then there's also a total mechanical energy chart here as well, right? So in the very beginning, it all starts with PE. It has a little bit of PE, gravitational PE, because the dart gun is not on the ground. And when it's way back here, it also has some elastic potential energy way at the beginning. All right, I don't know if we can get to like way at the beginning. You can see it's got PES in yellow, right? And a little bit of PE, gravitational potential energy. That immediately, as soon as it's fired, that PES turns into KE. And then the KE goes down and the PE goes up as it goes to the top and then back around on the bottom. But the total mechanical energy stays the same, because there is a closed system and there is no friction. Okay. All right. We will talk about if there is work next time, and we will talk about how to actually solve problems with kinetic energy next time. With conservation of energy. But for now, that's it. All right. So, peace out.